Hey, so I'm Mason Placatica, and this is going to be my Chem 3481 final project presentation. I chose to do an analysis of a paper from the Orlando lab. So this is radiation processing of formamide and formamide water ice on silicate grain analogs. It's a paper by Dr. Orlando and Dr. Dawley from the Orlando lab. So this paper had quite a few objectives, actually. The primary objective, as you would guess by the title, is just an investigation of formamide and formamide water ice materials on silicate grains through various methods. And the methods that were used for investigation were both photon irradiation and electron irradiation. And by the use of this irradiation, the goal of the paper was to characterize complex organic molecules like formamide and the decomposition of these molecules upon irradiation by both Lyman alpha irradiation and electron gun irradiation. And this decomposition and just the various side reactions seen upon irradiation were characterized via use of Fourier transform, infrared spectroscopy, and temperature programmed desorption across the scope of the experiment. So before we get into the experimental portion of this paper, just go a bit into the background and motivation behind the paper itself. So, ice, extraterrestrial ice in this case, exists and is fairly common in many regions of space. So, whether it be on man made or natural satellites like those we've put up orbiting Earth, or on natural satellites like the moons of planetary bodies themselves, interstellar dust, and ring grains on planets like Saturn or Jupiter, and especially on observable comets within our solar system. Ice is a common and well noted occurrence in space. Now, because of this and its commonality in space, exposure to various forms of energy and radiation is common for ice, be it water based ice or formamide or other organic ice, as seen in this paper. And once complex molecules have been introduced to this energetic radiation, sputtering and dissociative electron attachment and other side processes can occur, allowing for the formation of complex first generation molecules such as formamide, which is studied in this case, and allowing for numerous molecules that you wouldn't expect to be found in ices to be seen and observed. So, in order to replicate the conditions that would be experienced by formamide and other types of ices in space and on extraterrestrial planetary bodies like Titan, an ultra-high vacuum chamber, or UHV as it's abbreviated here, was constructed to operate at very low temperature and pressure ranges, like in the microtorr range of pressure, to simulate the vacuum that would be experienced in space. This chamber was coupled with a quadrupole mass spec and an FTIR spec for the temperature program desorption and the Fourier transform spectroscopy, respectively. And the samples, once placed in the UHV, were induced via radiation from a hydrogen flow lamp and a tunable electron gun. And these provided radiation in the Lyman alpha range and just energized particle ranges, respectively. Now, the irradiation of the formamic acid, performed by both the hydrogen flow lamp and the tunable electron gun, occurred once it was introduced to fumed silica nanopowder. And this nanopowder, while not perfect, is a fairly reasonable analog for the dust particles and grains that would be found in space or on planetary satellites like Titan and regions of interest. So, as noted previously, the first form of radiation induction performed on the sample was via a hydrogen flow lamp. Now, this hydrogen flow lamp was built specially to produce Lyman alpha radiation, which operates at the 121.567 nanometer range. And Lyman alpha radiation is the characteristic frequency of the N2 to N1 fall of an electron in a hydrogen atom. This form of radiation, while incredibly specific, occurs on a large scale, particularly in interstellar regions. There are large interstellar bodies that are characterized only by the fact that they emit large bodies of Lyman alpha radiation. So, as such, it is reasonable to conclude that much of interstellar ice will be exposed to Lyman alpha radiation at one point or another. Now, this being a resonant line source coming from the hydrogen flow lamp only operated at the one particular frequency and was conducted through microwave excitation of hydrogen, which, while only 2% in the gas flow through the lamp, was enough to get photon flux calculated to be somewhere around 2.7 times 10 to the 14th photons per second, and induced high levels of radiation and energetics in the sample across the board. Now, the second method for sample irradiation for this experiment was via a simple electron gun. Now, this simple electron gun just used hot cathode excitation of a supply system and focusing through numerous lenses to form an electron beam that was somewhere around 1.5 millimeters. Now, this size, while not incredibly focused, was enough to irradiate the sample for the 72-hour duration of the experiment, and in the range of 5 to 1,000 electron volt electrons. The current density at 1 kiloelectron volt operation was calculated to be somewhere around 10 to the 14th electrons per centimeter squared per second, which, as with the Lyman alpha radiation, was more than enough to both excite and characterize the sample over the 72-hour period of the experiment. So, upon irradiation via both methods of the formamide and formamide water samples, numerous spectra and results were able to be obtained. So, as seen to the right here in figure 1, decreasing formamide and corresponding formamide water emission was seen upon both forms of increased radiation exposure and increased radiation time. So, this to say that the more radiation that was experienced by the ices, the more organic formamide and water decay was seen. Upon this decay, side products like the negative OCN, which is the cyanate anion, and carbon monoxide signature increases were observed. So essentially, this is to say that upon radiation exposure, complex molecules degraded into more simple and volatile species. The cyanate anion formation was more efficient upon electron irradiation than upon photon irradiation, which is likely due to the simple energetic difference. The electron irradiation is far more energetic and focused than the photon electron irradiation. Now, the induction of side reactions was also noted far more highly in the electron radiation of the formamide water ice than formamide itself. This is a precursor to further experimentation to characterize these side reactions, but shows some sort of stability or stabilizing reactions caused by the presence of water. Due to the limited scope and very focused objectives of this experiment, there were not a great deal of limitations. However, one notable limitation was the use of the silica grain analogs. While these silica grain analogs and the nanopowder particle used in this experiment have been noted as a reasonable analog for the silica grains seen on extraterrestrial bodies and in space, they have a very limited breadth of chemical composition, and the lack of other inorganic compounds could limit further catalysis or further side reactions, which would be noted in actual space. The radiation limitations of the experiment were fairly obvious in the fact that only 2 forms of radiation were used. Other common forms of radiation seen in space, such as high levels of gamma and microwave radiation, were not covered in this experiment, simply due to scope and the availability of time and equipment. And the side reactions in the formamide water cases, while noted, were not characterized by this experiment. Beyond the simple scope of this experiment and its objectives, there are quite a few other applications for what was used, both in terms of information and experimental setup in this experiment. So first of all, the methods used in this procedure can be used for characterization of other first-generation molecules. While formamide is one of the most primary and noted first-generation molecule, there are numerous other complex molecules which can be found in extraterrestrial environments. The methods used in this experiment could also be used to characterize the side recombination reactions, which can result from the degradation noted in this procedure, particularly in the water formamide ice analogs, and the molecular reactions upon exposure to strong ionizing radiation in low-pressure environments is a problem that exists not only in space, but in our terrestrial atmosphere, and the forms of analysis, both the temperature program desorption and the FTIR upon radiation, could be used to measure terrestrial atmospheric reaction upon interaction with both internal and external ionizing radiation.